All right, so our first speaker today comes to us from Caltech. This is Gavin McCabe. Gavin's a rising sophomore there, and he's been working over the summer with Shuvo on a project entitled Machine Learning-Based Morphological Classification of Type 1a Supernova Host Galaxies. You can go ahead and get started whenever you're ready, Gavin.
Thanks, Gwen. Thanks for the introduction. I'm really excited to speak here today about my work this summer using machine learning to solve a big problem in astronomy. So let's see. So first, let's quickly talk about what galaxy morphology is and why we really care about it. So galaxy morphology is important because it provides hints on structural, intrinsic, and environmental properties. For example, early type galaxies, or what we're going to classify as elliptical galaxies, are going to tend to have a larger mass, less gas in them, and older stellar populations, whereas the late type galaxies, what we're going to consider spiral galaxies, are going to tend to be rich star-forming galaxies. So lots of stars are going to be formed inside of those spiral galaxies. Mapping the late type galaxies or the spiral galaxies are going to help us to map the universe and its expansion, which is a huge field of study. And these can tell us a little bit of insight on how these galaxies are formed, which gives us a lot of information about the history of the universe. And finally, we're going to talk about possible correlations with supernova properties. So for example, supernova from the fastest decline rates tend to be located in the elliptical galaxies, where supernova from spiral galaxies tend to have lower distance moduli. And supernova in late type galaxies or the spiral galaxies tend to be more homogeneous than supernova in the early type galaxies. So I've talked a lot about galaxy morphology, but what exactly is galaxy morphology? Well, in simple terms, it's the shape of the galaxy and what it exactly looks like. So we can talk about tons of different things. For example, we can talk about the shape of the galaxies. In here, we can see there are two major groups that we have. We have spiral galaxies over here, and there are elliptical galaxies over there. And these are the two main categories we're going to be using today. We can also talk about bars that galaxy might have. So you can see here on the bottom, I pointed to a galaxy that might have a bar in the center of it, of either mass or various gases. We can talk about the spiral arms in a galaxy, so how closely they're packed, how many of them there are, how far they spread, etc. And we can talk about the different bulges. So some galaxies will have bulges in the center of them, like this one right here. So looking at galaxy morphology, we can tell a lot of different things about galaxies, like I showed before. But we need to actually see how it's done. How do we actually classify galaxies? Well, right now, the way that we do it is with volunteer scientists through programs like Galaxy Zoo. So Galaxy Zoo allows citizens just to come online and look at galaxies and say, hey, this looks like an elliptical galaxy, which is great, but presents a few issues that we'll talk about in just a moment. Grad students also commonly classify galaxies, although it's not nearly on the scale as Galaxy Zoo. So we'll also talk about that. So the big problem is that there's over 357 million photometry sources released in the Sloan Digital Sky Survey data release 7, just as of 2018, and this is before any new surveys come online. So this is a lot of data that we have to deal with, and over 15 terabytes of data will be released just in this one survey when it's complete. So this is just too much data to work with. We don't have the human power to go through all these data and look at it and classify all of these galaxies. So because of that, visual classification is out the door. It's not viable anymore. So we have to look at new methods, and I present using machine learning, artificial intelligence, and image classification to do this automatically. And you'll see a little bit later how this is actually going to be done. And in the end, we want to create an automated classification pipeline. So galaxies are automatically fed from the telescopes and surveys directly into my system. They're automatically classified, and then they come out the other end pre-classified with no human intervention is the final goal. There are systems that have done this in the past, such as a software called Galfit, but it requires at least 22 different inputs from the user, and this takes a lot of time. So this just isn't very useful at the moment. So I'd like to present a way of doing this with only 2 parameters. So what do we need for machine learning to work? Well, first we need objective parameters. We need some numbers we can work with. Images are great, but numbers are even better. So we're going to look at SciMorph in just a moment and see how that can help us. Next, we're going to need training and testing data. So this is going to come from the Carnegie Supernova project, as well as the Sloan Digital Sky Survey. And these are going to be galaxies that have been classified through the program Galaxy Zoo I talked about before as either spherical or, spiral or elliptical galaxies. And these are pre-classified. So I just have a list of thousands of galaxies that are either spiral or elliptical. And finally, we need the actual machine learning algorithm, which we'll be using support vector classification. Again, we'll talk a little bit more about this in a moment. So let's talk a little bit about SciMorph and what it actually does. So we basically give it a photo of a galaxy, as I've shown here on the right, and it gives us some information about the asymmetry, the smoothness, gradient pattern analysis, Shannon entropy, and concentration of this galaxy. And it's a good estimation of some of these parameters in real life. So a couple of these that we can look at are asymmetry, tells us how asymmetrical the image is. So this can tell us things about galaxy arms, spiral arms. We can also look at whether something's elliptical, if it's more spherical, or if it's a little bit more squished. That can tell us a little bit about that. The smoothness tells us a lot about spiral arms, because if there's spiral arms, the image will be a little bit less smooth because it'll almost look like zebra stripes as we have this the spiral arms coming out from the center. The gradient pattern analysis tells us a little bit about how the gradient is on the image. So that's a little bit more of a computer science technique used to look at the gradient of the image. And finally, the Shannon entropy talks about how random this image is. So this can be used to look at the randomness of pixels in the image, or to tell us a little bit about the background of the image, etc. So we basically give it this image that I've shown up top, and it goes to the algorithm and gives us just a list of parameters out the back end. And these are on different axes and with different parameters tweaked a little bit, but they're all based off of these five main parameters here. So this is the way that we take an image and convert it into actual numbers that we can use. So some people ask, well, how do you actually get an image of a galaxy? It seems a little bit simple at first, but it turns out to be a little bit more complicated. So we need to use something called object detection. So what exactly does object detection do? Well, we can start with a field that looks something like this. And most of us can probably locate the galaxy located near the center, but it's a little bit harder to do this automatically with no human intervention. So there are lots of sources, stars. Looks like there's some sort of glitch in the center of the image. So we need to really get rid of all of that and just get a picture of a galaxy. So the next step is my algorithm looks at all the sources, and it takes away the background, takes away everything, and just decides where these actual sources are. So it color codes everything. You can see there's stars and the galaxy is the big object, and gives us all of the sources. Well, this is great, but we need one more thing. We need to actually find out where the galaxy is. So we can cross-reference with the other parameter given by the astronomer, the coordinates, and we can cross-reference where the actual galaxy is located. So in this case, we cross-reference it to this object here. And finally, we can take just a stamp of that on the original data, and we get this beautiful image of a galaxy here. It looks like a spiral galaxy in this case. So this is how the object detection algorithm can actually take a field given directly from a telescope and turn it right into a beautiful image of a galaxy that we can work with SciMorph. So right now we have detecting the objects and then automatically parametrizing them using SciMorph. So the last step is the machine learning algorithm. So how does machine learning really work? Well, it works just like you and I learned. It takes images that it knows are spiral and knows are elliptical, and it basically just shows it. This is what a spiral image looks like. This is what an elliptical image looks like. And it's going to try to figure out the best way to determine between them. Just like how you and I learned the difference between a stop sign and a yield sign, it does the same thing. We just give it example after example. So in this case, we have the pre-classified data that I talked about before, the 500 elliptical and 500 spiral galaxies from Galaxy Zoo. And we're going to use an algorithm called support vector classification, or SVC. SVC tries to find the optimal hyperplane that divides the classifications. In layman's terms, it basically just tries to separate the groups as best as possible. So it sees that all of these must be elliptical, all of these must be spiral, and it just kind of figures it out from there. So it's really hands-off, which is really nice, and it works well with smaller data sets like this. And finally, it can actually make the prediction given certain parameters by SciMorph, whether it's going to be spiral or elliptical. Right now, I've used 1,000 galaxies, but in the future, we'll be training it on 101,000 galaxies, all from Galaxy Zoo. So here's kind of the final pipeline that we're looking at. We start with the image, the field image right from the telescopes, and we put it into the cutting algorithm, which I talked about before, which detects the object and cuts out a picture of that object. Next, we're going to use the SciMorph algorithm to take the image and actually get numbers out of it in the form of a CSV file. And finally, we're going to use the machine learning algorithm, the SVC algorithm that I talked about before, to actually classify whether or not it's going to be a spiral or an elliptical galaxy. So all at once, it can take just the coordinates and the field of the galaxy and automatically detect whether it's a spiral or an elliptical galaxy. And with all this, it's 93.4% accuracy, has a 93.4% accuracy in the end. And accuracy here is defined as agreement with the Galaxies classification, which is great. And this is only trained on 1,000 galaxies. In the future, we'll be doing 101,000 galaxies. And like I said, this only takes 2 parameters, the coordinates and the image, unlike the 22 that GalFit uses. And research does show that when I upgrade the number of training sets that I'm using, this algorithm will have over 99% accuracy. And I did find that the most prominent factors are the smoothness and asymmetry of those parameters that we spoke about before. And some people have asked, well, what does that actually look like, the ones that it gets wrong? Well, this is something that it classified incorrectly. It classified it as spiral when it was elliptical. And you can see that this is very blurry compared to the other objects that we've seen before. So with more training, it's definitely possible to get these correct, but you can see that the ones that it's getting wrong are very, very difficult to classify even by hand. So this isn't something I'm too worried about, although these problems will go away as we have more classification data. So the final pipeline is going to take automatic data retrieval and classification. So we're going to get data directly from telescopes and sky surveys and automatically classify the galaxies within them. We won't have to wait for humans to classify them, and it'll be almost instantaneous. It only takes a couple of seconds. So in conclusion, galaxy morphology provides information on formation of galaxies, dark energy composition, expansion of the universe, etc. And it can give us a lot of information possibly about possible supernova host galaxies and the properties of the supernovae inside of those host galaxies. The automated classification algorithm and pipeline is going to be huge. It's going to make it so we don't need to rely on humans anymore, and it will make this a lot faster and a lot more viable, especially as things such as LSST come online with more and more data that we just cannot handle. I'd like to acknowledge all of these people for helping me this summer, and I'm happy to answer any questions if there are any. Thank you for listening.
Nice job, Gavin.
Thank you.
All right, do we have questions? You can either unmute yourself and ask, or you can raise your hand either. Well, you'd have to raise it in the participants window. I can't see everyone.
Gavin, I have a question. Do you hear me?
Yes, I can.
Okay. As the distance of the galaxy increases, like the last example you showed, details get more and more smeared out. In some way, that must affect the ability to detect whether there's spiral structure or not. Have you looked into what the redshift might do in terms of systematically shifting from spiral galaxies to ellipticals, even if it's not necessarily a physical shift?
Yeah, that's a great question. I haven't looked at that exactly with the redshifts, but I am definitely working on getting more examples of these galaxies that might pose some of those difficulties. Like I said, right now everything's based on the Galaxy Zoo classifications, so I haven't looked quite into the redshifts and stuff like that, but that's definitely something I'm willing to look into in the future because that definitely can have an effect.
Okay, thank you.
Great. John, do you have a question?
Yeah, I was just wondering if you've, what it does in the case where you might have a galaxy merger or 2 galaxies very close to each other. Have you looked at a lot of those, or does that complicate it, I assume?
Yeah, so that's something that is definitely possible, and I'm looking into implementing. Right now, it would just kind of give an error that it doesn't really look like either one of them, the spiral or elliptical, because we look at it all at once. But I do have training sets ready to classify 2 galaxies at once, so I'm getting very close to implementing that as well.
Great, thank you.
Any other questions for Gavin? All right, very nice job, Gavin. Thank you.
Thank you.